In this video, we are going to do some examples involving evaluating double integrals using polar coordinates. Okay, so let's get right into an example. Let's say I want to evaluate this double integral. So there's a few tip-offs that I might want to try using polar coordinates. We've already seen an example in the last video where something like this negative x squared minus y squared showed up. Because if I factor out a negative, I'll get e to the negative and then x squared plus y squared. And that's really nice in polar because this becomes e to the negative and then that sum of squares is just r squared. So that's one of the tip-offs that I might want to try polar coordinates. Another tip-off is based on what this region looks like. So I'm going to get that part started for us, and then I'll have you pause it in just a minute to try it. So let me draw some axes. So my y-axis, my x-axis. And if I look at this upper limit of integration, so this inner integral is based on y. So I'll look at the equation y equals square root of 4 minus x squared. And that's the graph of a semicircle. One of the ways I can see that is if I were to square both sides, I would get y squared equals 4 minus x squared. And if I move the x squared to the left, I'll get x squared plus y squared equals 4. And I know that's the graph of a whole circle. So why is this one a semicircle? Well, it's because if I reversed my steps and I went from here to here by square rooting both sides, technically I would get a plus or minus. I would get a plus or minus in front of the square root. So because there's no sign in front of my root, it technically means this is outputting a non-negative value. So that is saying y equals a non-negative number. So on my circle, I'm only on the part of it where y is non-negative, which is the upper semicircle. Okay, so this is the upper semicircle. So I will sketch that in, where the radius is 2, because r squared is 4. So 2, and that's negative 2. Okay, and then from there, I want to have you try it. So see if you can draw this bottom curve, and then sketch that region of integration, and continue from there, convert it to polar. So pause it for about 4 minutes to try it. Pause in 3, 2, 1, pause it and try it. Okay, so hopefully you did that. Hopefully you paused it to try it. So this lower limit of integration, y equals the negative, and then of the square root of 4 minus x squared. We kind of talked about that alongside this one. That would be the bottom half of this circle. So it's the bottom semicircle, where this hits at negative 2. So, okay, so I have my bottom curve, and I have this upper curve. So now the outer integral, dx, is based on these two values. So x is starting at 0 and going up until 2. So if I shade in that region between this upper and lower curve, that's this region here, the right half of this circle. Okay, so nice. I have my region of integration. So if I want to convert this thing to polar coordinates, one of the other tip-offs that's nice to do is circular regions are super nice in polar form. So my circle equation in polar coordinates, remember, it's going to be r equals, well, what's the radius of that circle? It's 2. And that's just a super simple equation in polar form. So, okay, let's convert our double integral. So our double integral, I know that my function simplified to e to the negative r squared. We've already seen that the dy dx, another way to write that is dA. Well, in polar, that becomes r dr d theta. And then I need these limits of integration. So the inner integral is based on dr. So to find those limits, I draw a line radially outward from the origin. So where does it enter the region? Well, it enters the region right away. And at that point, r is 0, because our distance from the origin is 0. And then it exits the region here, which is on the curve r equals 2. And that's my upper limit of integration. Nice. So instead of having these complicated looking lower and upper limits, now our limits of integration are just constants. So that's definitely simpler. And then the theta limits of integration for the outer one, well, where does theta start? So theta kind of starts here, and then it keeps going up until this point. So it starts at negative pi over 2. So theta equals negative pi over 2 up until theta equals positive pi over 2. Positive pi over 2. Okay. If I wanted to not write the theta equals and the r equals for these, I could. It's clear from the order if they go with r or theta, but just because we're first learning this and practicing it, I'm going to go ahead and write those. So, okay, because these limits of integration are constants, and I could split up this function into a part purely with r's and a part with thetas. The part with theta would just be, there's a hidden 1 here. I could decouple this integral if I wanted to, but just for practice, let's do it without decoupling. So I'll get my outer integral, which goes from negative pi over 2 to positive pi over 2. And then for the antiderivative of e to the negative r squared times r, we could do a u sub on this, but let's practice doing this by, what I call some educated guess and check. I know the antiderivative of e to the stuff like this often has e to that stuff in it, but let's check if this is right. I know the derivative of e to the stuff will be e to that stuff times the derivative of this stuff, which will give me a negative 2r. But I don't see this extra negative 2 factor in my function up here. So I'm going to need to cancel out that negative 2, and I cancel that out by putting a negative 1/2 in front. Okay, so I'm going to put a negative 1/2 in front. Now, if I take the derivative of this, I will get the function that I have here. Okay, so I did a little educated guess and check, some trial and error to get that. Okay, that's my antiderivative. I then got to plug in r equals 0 and r equals 2, and then d theta on the outside. So now when I plug in, I got the outer integral from negative pi over 2 to positive pi over 2. When I plug in, I'll get negative 1/2 e to the negative 4, and then minus, when I plug in 0, I'll put a parentheses, I get this negative 1/2 e to the 0 is 1, so just negative 1/2. Cool, and d theta. So what I have here now is just a constant in my integral. And the antiderivative of a constant is, well, it's that constant times theta. So this constant, this whole thing, times my variable, theta. And then I got to plug in the values for theta. So negative pi over 2 to positive pi over 2. So we'd now plug these in for theta, and then I'd subtract. I'm going to trust that we can do that and simplify that. So I'm going to kind of do 2 steps in one, the plug in and simplify. If you do that, you'll get negative 1/2 e to the negative 4 plus 1/2. And after some simplification, I'll end up with just pi on the outside. And that's my value for this integral. So the tip-offs, again, that using polar coordinates was helpful was, well, in my function, I saw this r squared popping out. And then this region of integration involved a circular portion. And that's really nice in polar coordinates. All right, so let's end this video with one final example. So we are going to look at a really classic example, which is the integral from 0 to infinity of e to the negative x squared dx. It turns out that it's impossible to evaluate the antiderivative of this function in terms of what are called elementary functions. Those are functions that I know, like exponentials, logs, trig, and combinations of those. But there is a cool trick that we can use given that this is now an improper integral. It's going to infinity. So in this video, I want to introduce you to what that trick is. I'm actually not going to fully work out this example because it's actually a homework problem to do this example, but I want to get it started together for us. Okay, so here's the idea. I'm going to let this integral be equal to I, and I'm going to square I, which means multiply it by itself. When I do that in the second integral, rather than calling the variable x again, I'll just relabel it and call it y in the second one. And the nice part about doing that is, because now I have two integrals multiplying each other, one that's purely in terms of x, one that's purely in terms of y, I get to sort of combine them into a double integral. This is the opposite of decoupling them. So 0 to infinity, and then the other one 0 to infinity. Multiply the functions, e to the negative x squared times e to the negative y squared, and then dx dy. So we're reverse decoupling to combine them. Okay, and then, well, this thing inside can get simplified. This becomes e to the negative x squared minus y squared. Oh, and if this is looking familiar, this negative x squared minus y squared, we've seen this so much already in this section. Well, that's one of my tip-offs. So my idea is going to be, well, switch this thing to polar. So switch to polar here. Switch to polar coordinates. Okay. What I'm going to end by saying is, well, let's think about this region of integration. So if I draw my axes, the inner integrals in terms of x, the x limits go from 0 to infinity. Even the y ones go from 0 to infinity. So in my picture, that's actually this whole first quadrant. X going 0 to infinity, y going 0 to infinity. It's everything there in that first quadrant. X goes from 0 to infinity, y goes from 0 to infinity, everything there. Okay, so when I convert to polar, I'll have to think about, well, how do I express this region in polar coordinates? All right. The very last thing that I'm going to say, and that's where I'll leave this off for you to try to finish on the homework, is, where do functions like this show up? Because they're actually quite common in statistics. So if I think about drawing this, it turns out the graph of y equals e to the negative x squared, it has the following shape. Kind of goes up like this, has like a high point at the x on the y-axis, and then it kind of is symmetric across the y-axis. And then it has these asymptotes. It snuggles up next to the x-axis as I go really far out. So in statistics, you see functions like this show up all the time in the context of the normal distribution. And we're particularly interested in figuring out what the area is under this graph. And that's actually kind of the point of this example, to find a method for doing that. And interestingly, it actually involves multivariable calculus. I somehow need to cleverly use these double integrals to get the value. So you'll continue this in the homework to figure out, well, what is that actual value? So in terms of our goals for this section, we finished our last goal, recognizing when and how we use polar coordinates to evaluate double integrals.